Okay, so just continuing from the last video, now we're going to talk about how we can depict the electric field in a diagram, okay, using vectors and also using electric field lines. And again, to remember, the electric field really is more like a fluid. It fills the space that's everywhere, but practically speaking, when we're trying to draw it in a diagram, right, we can't really do like what that PhET simulation did and have this like nice color gradient to represent a decrease in the magnitude of the field. It's more practical for us to just draw lines and arrows. Okay, so let's say we've got two positive charges here, and I want to depict the electric field around these two positive charges. Okay, the first thing I could do is draw some vectors. Okay, so we'll draw some electric field vectors, okay? And they are going to show the magnitude and the direction of the field at specific points. Okay, in particular, where the vector's tail is. All right, and I'm gonna scooch this down a little bit. Okay, so when I'm drawing these field lines, I want to consider what the electric field actually does. Okay, I know that the electric field, it points away from positive charges, because really it depicts the direction that a positive charge would move in the field, and a positive charge is going to be repulsed by another positive charge, so it's going to move away. Okay, and for the same reasoning, it points towards a negative charge. Okay. And I also know that the magnitude, or the size of my vectors, is going to drop or decrease, okay, like 1 over r squared. Okay, so when I'm drawing these vectors, I might not perfectly, I'm not getting a ruler out, so I might not perfectly depict that decrease in the magnitude, but hopefully the intention will be there. Okay, so I'm going to draw some points, okay, where I will depict the strength of the field here around this charge. Right here and here and here. Okay. Let me scooch this guy over just a little bit. And we'll do the same thing over here. Okay, and now I'm just going to draw those vectors. So again, they're going to be pointing away from positive charges. They're going to get smaller as I get further away. So if I wanted to try to do this really precisely, this should be about 1/4 as long as the other one. So something like that. Okay. Do the same thing over here. You guys are picking this up, it might be a good time to skip forward in the video. That's what you can do with these video lectures. You guys are in control here. Okay. All right. I drew a bunch of vectors. All right. So this is one way I can represent the field, right? It tells me the strength and the direction of the electric field at these specific points. Okay. So there's another thing that I can do that's commonly used, another technique to depict the field, and that's to draw field lines, okay? So to draw the field lines, what I'm really doing is I am kind of connecting or tracing through these electric field arrows are these vectors. So I'm going to connect arrows to trace out what's called a field line. Okay. And the lines, the direction of the lines, okay, the lines are going to show the direction of the field at each location along the line, okay? So what that means is if I were to go through here and draw those field lines, I'm just going to kind of trace through those arrows here. All right. Oh, you know what? I wanted to make this a negative charge, so bear with me here, actually. I'm going to switch all this around. My mistake. That's going to make this a little bit easier to draw. And okay, that just makes this line a little easier to draw. Okay. And notice with these field lines, I am putting arrows at just the very end of them. You can also put arrows to indicate the directions, just kind of intermediate like that. Because you do want to know the direction of the field depicted by the lines. You just don't want to draw a line without that directionality to it. Okay, so you'll see different ways to do this, diagrams in the book, but usually at the end and sometimes in the middle, something like that. Okay. So I drew some field lines. If I draw them at regular intervals, okay, then the density of the field line is going to, indicate the strength of the field. Okay, so for example, I didn't draw force vectors here, but I know that the field, if I did have force vectors, I know that the field would do something like this here and this here. Okay. It's going to connect kind of like that and like that. Okay. So what does it mean to have regular intervals? Well, here, if I look at around my positive charge, I've kind of drawn these at a regular distance along the circle. Okay, so now if I look along this part of close to my charge, I've got a higher density of field lines, so I've got more concentration of field lines here, and then as I get further away, right, the concentration, the number of field lines, say, per arc along this circle is decreasing. That shows that the electric field is decreasing with distance, okay? Without actually having a length of the arrow, I can indicate that with density of the field lines. It doesn't work like over here on this diagram. I haven't drawn the field lines at a regular interval. I drew, right, a bunch over on this side, and then I was lazy and I didn't draw any extra ones on this side. So it's going to look like, right, the field is maybe weaker over here than it is over here, which isn't true. It's just I haven't drawn the diagram correctly. Okay, so in order to make this correct, I would have to draw a couple more field lines on this side depicting, right, this part of the field, and now it's going to be at regular intervals. And let's see, let me do that a little better. Okay, and now if I say compare the density of field lines around, screwing up here, around this charge to this charge, it's about the same, which indicates the field strength is about the same, which is what it should be. Okay, so let me just write a few notes on that here. If drawn at regular intervals, okay, the density of field lines indicates the strength of the field. Okay, and again, this is all review from 183, so hopefully it's a little bit familiar. Okay, there are some rules with field lines, so I want to talk about that. Okay, for a moment. It's important that we, again, know how to draw these. I'm just going to scooch this over. I'm going to write the rules up here just because I'm running out of space. Okay, so these are pretty important. There's some rules. Okay, the first rule is that field lines, they cannot cross. Okay, I cannot have, for example, right, a field line going through that field line like that. The reason is that implies at this point, okay, let's say I'm going to draw up like an arrow here. That would imply at this point the electric field is both pointing to the right and up and to the right, okay? And that's not possible because of superposition. You only can have one direction and one magnitude of the electric field here. If that electric field is due to multiple charges, then it's just going to be the result of the superposition of all those electric fields, but it can't have multiple directions and multiple strengths at a single point, okay? So the field lines cannot cross, all right? So that's not allowed, okay? And the second rule is that field lines are either closed loops, or we'll just say closed because they're not really, oops, I didn't draw it. Okay, they're either they begin or end on a charge, okay, or they extend to infinity. Okay, so these field lines here, if there was really just two charges in space, like these field lines would be examples of field lines that extended to infinity. These ones are examples that begin and end on a charge. Okay, those are our rules. That's what we want to remember about drawing these kind of diagrams that represent the electric field. And remember, these field lines, even though they're super useful, I use field lines all the time in my research, they aren't really real, okay, because a field is like a fluid, but really they are a tactic for depicting a field in a diagram.